Hi everyone, and thanks for joining us today for our webinar, Power of LCA in the Built Environment. We are excited to be amongst such an exemplary group of architects and designers and manufacturers. My name is Kim Vincent, Sales Executive with SCS Global Services, and I'm joined today by Jeremy Haken, LCA practitioner with SCS. Our whole intention for putting this webinar on today was we've heard a lot of people talking about EPDs and saying that it's just an exercise where we just check the box. Have you ever asked yourself that? Today's webinar is to help you understand the power behind the LCA. I've worked at SCS for 5 years, and I've had the privilege of working alongside our LCA practitioners. And amongst a whole bunch of candid conversations with people such as Jeremy, I have learned a lot about materials in the built environment. My view has changed from that which might be one similar to an architect or maybe even a manufacturer to one of more an LCA practitioner. So we're very excited to share with you our insights and our perspective of building materials from an LCA lens. So before we get started, a few housekeeping items. If you have any questions, feel free to type them as we go via the chat window, and we'll respond to them at the end. You are muted, so if you are experiencing technical difficulties, please use the chat function or shoot me a quick email, kvincent@SCS Global Services. And this webinar is being recorded. You will have access to it shortly afterwards. So Jeremy has worked at SCS as an LCA practitioner for nearly 3 years, focusing on building construction materials and interiors and finishes. Formerly, he modeled energy systems at Booz Allen Hamilton, and he also investigated the life cycle of alternative fuel options for Patagonia clothing for his master's thesis.
Thanks, Kim. So this webinar will provide unique insights from a practitioner's viewpoint on potential environmental impacts of building materials and ultimately provide a better perspective on material impacts, product design, and manufacturing. As LCA practitioners, we already have a loose idea of the potential environmental impacts of a product before even completing the study, a so-called LCA lens. If I can help you see through this lens, you would have some preliminary insight on the potential environmental impacts of product systems. However, this lens only gets you so far, since there are exceptions that are only revealed upon completing a LCA study. We'll also cover some of these exceptions in this webinar. In today's presentation, we'll be discussing 3 main topics. In viewing building material products from an LCA lens, we'll be spotting trends and understanding their influencing factors. In interpreting LCA results, we'll be identifying the important information in an LCA or an environmental product declaration to understand the major basis for how results are reported. Lastly, in surprising finds, we'll look at some interesting results we found from a few LCA studies that ultimately show that there are exceptions and that LCA is a powerful tool in understanding our built environment. Life cycle assessment is a scientific and engineering discipline to assess potential environmental impacts associated with the product throughout the stages of its life cycle. A cradle-to-gate study represents the stages from raw material extraction and processing up to the assembly or manufacturing of a product. A cradle-to-grave study represents all stages of the life cycle, from raw material extraction up to the disposal of the product or end of life. When conducting an LCA specifically for the development of an environmental product declaration, a product category rule is used to scope the project and establish the life cycle stages and system boundaries of a product category system. An environmental product declaration, or EPD, is a transparency document that summarizes results of an LCA to a standard format required by the corresponding product category rule. In a word, a product category rule is used to develop the life cycle assessment, which gets summarized in an environmental product declaration. We've actually just recently hit our 100 mark for published environmental product declarations. After conducting and reviewing a multitude of LCA studies, certain trends can be spotted. These trends reveal several factors that typically influence the results of an LCA study. Identifying and understanding the trends we can see provide preliminary insight prior to conducting an LCA or interpreting its results. The graph here shows the percentage of total impact by life cycle stage for environmental impact categories. The impact categories shown here are those that are typically reported in an environmental product declaration and are derived from the US EPA's characterization method, TRACY. For the examples presented throughout the remainder of this webinar, the global warming impact category will be used to represent potential impact. The life cycle stages listed on the right of the graph cover the entire life cycle of a product from cradle to grave, which include raw material extraction and processing, production, distribution, use and maintenance, and end of life. Each bar in this graph represents the contribution of each stage to the total result for the specified impact category. For example, the contribution of raw material extraction and processing to the global warming potential of this product is approximately 65%. Although results here happen to be for a specific product, in this case a demountable wall, they represent a trend that is observed for most building products. Essentially, that upstream from manufacturing, the raw material extraction and processing of those materials, shown in orange, which are used in the assembly of a final product, typically have the largest contribution to environmental impact. This stage includes extraction of virgin materials from the earth, or from post-consumer or pre-industrial sources, the processing or refining of those materials, and their delivery to the product assembly site. Examples include ore that is mined and converted to base materials, crude oil that is extracted and processed into base chemicals, or trees that are grown and harvested for lumber. The major influencing factor for this trend is the material type used in a final product. Some of the most common building materials used today require energy-intensive processes upstream from manufacturing to produce the components supplied for final product assembly. If we're familiar with the carbon intensity of common types of materials that might be used in the assembly, we gain quick insight into the potential environmental impacts over its life cycle. The graph here shows the relative global warming potential, abbreviated as GWP, and expressed in kilograms of carbon dioxide equivalents for several common material types. Carbon dioxide equivalence is a term for describing different greenhouse gases in a common unit. For any quantity of greenhouse gas, carbon dioxide equivalent signifies the amount of CO2, which would have the equivalent global warming impact. Results in this graph are shown per kilogram extracted and processed material. Essentially, results here are shown on an equal basis. It is important to note the dramatic difference in GWP between processed virgin material extracted from nature and recycled material. In this instance, shown in blue, we see the difference between primary aluminum versus recycled aluminum. Similarly, shown in gray, there is also a large difference between carbon steel produced in a basic oxygen furnace versus steel produced in an electric arc furnace. In an electric arc furnace, final product is formed predominantly from steel scrap. As such, material substitution or dematerialization in a final product can have an outsized influence on LCA results. In addition to the type of material used in a final product, the amounts of materials used have a substantial influence on this trend. The tables at the top show two scenarios for alternative material compositions of hypothetical chairs. Material type is reported by row, and the columns report the corresponding amount used in each chair. In the table on the left, steel components are being added to the base chair, ultimately increasing the total weight of the chair and the amount of steel being used. The steel used in this example is steel produced in an electric arc furnace and is therefore high in recycled content. Similarly, in the table on the right, plastic components are being added to the base chair, ultimately increasing the total weight of the chair and the amount of plastic being used. Since steel components weigh more than plastic, chairs 2 and 3 have a larger increase in weight than chairs 4 and 5. Despite the differences in material amounts used, each chair provides the same function to seat one individual. The graphs below the table show the relative GWP and is expressed in kilograms of carbon dioxide equivalents per chair. Results shown represent the total impact due from extraction and processing the materials upstream. Impact does not include fabrication of chair components, the assembly of each chair, or any other downstream process. In this example, the addition of steel components have a larger increase in impact than the addition of plastic components. Larger total environmental impacts are observed for products manufactured in particular regions of the globe and for products that need to be distributed over relatively long distances. The trend observed is primarily as a result of the electric power grid used, or the distance from supplier to the manufacturing facility, or from the manufacturing facility to a point of sale. The earliest electric utilities operated independently from each other and provided electricity through its own delivery system. During the second half of the 20th century, utilities found it more efficient and economical to connect their delivery systems, resulting in the regionalization of electricity supply mixes, which are coordinated by regional system operators to ensure reliability. Electricity is typically received from centralized generation or power plants that use a wide variety of energy resources to produce electricity, such as fossil-fueled power plants, nuclear power plants, hydroelectric dams, wind farms, etc. The environmental impacts of electricity use depend on the sources for its generation or the electricity grid makeup of the region. As a result, electricity delivered to consumers by their local electric utility may be generated at a centralized power plant located in another city or state and owned by a different company. The U.S. EPA's eGrid, or the Emissions and Generation Resources Integrated Database, is a comprehensive source of data on the environmental characteristics of almost all electric power generated in the United States, and it is typically used to represent the electric power grid makeup of a region in an LCA study. The subregions here represent the electric power grid's current structure. Let's for a moment consider two hypothetical electric arc furnace steel mills producing in Alaska and Illinois. These states fall under the following regions, respectively: AKMS, which is the Alaska Power Grid, and SRMW, which is the Circ Reliability Corporation in the Midwest. The graph here shows the relative GWP for carbon steel produced in an electric arc furnace and is expressed in kilograms of carbon dioxide equivalents. Results are shown per kilogram produced in each region. While it is for the same process, electricity is being sourced from a different electric power grid mix. Essentially, the steel mills are located in different regions of the U.S., performing the exact same process, all else equal. The bar shown in gray is based on the average electric power grid makeup of the U.S. We can see that differences in the electric power grid makeup can potentially have a substantial effect on the global warming potential of this process. In some cases, almost a 35% reduction or a 20% increase from the U.S. average. The main reasons for this is due to the supply mix, where the Alaskas is composed of approximately 64% hydropower, while Illinois is composed of approximately 72% coal. Let's transition now to the transport of material or product. The graph here shows the relative global warming potential for three modes of transportation expressed in kilograms of carbon dioxide equivalents, and results are shown per kilometer transported. Although transportation by ship or rail is more efficient than truck, materials or products shipped via these modes tend to be transported longer distances. Furthermore, although distribution of final product does not have the largest contribution to total environmental impact over the life cycle, typically between 5% and 20% contribution, products that need to be distributed over relatively long distances compared to local distribution of its equivalent competitor results in a larger environmental impact. For example, the freight transported by ship from Germany to New York is approximately equivalent in magnitude for the global warming potential to an equal amount of freight transported by truck from San Francisco to Seattle and Washington. Therefore, for some product systems, an additional supply or distribution leg requiring transoceanic freight can potentially double the contribution of transportation to environmental impact from this stage in the life cycle of a product. Similarly, the freight transported by truck from New York to San Francisco is approximately twice as large in GWP to an equal amount of freight transported by train. As such, utilizing more efficient modes of transport for longer distances can significantly reduce environmental impact associated with distribution of product. Furthermore, reducing the distance from manufacturing facility to customer or distribution center can potentially halve the environmental impact associated with distribution of product. Understanding the factors discussed can not only help anticipate demand and stay ahead of trends, but also elucidate perspective on material impacts in manufacturing prior to conducting an LCA or developing an environmental product declaration. We observed that sourcing from suppliers of raw materials for product assembly with lower impact dematerializing or substituting materials, utilizing efficient modes of transport, and sourcing from local suppliers can have an outsized influence on LCA results. When interpreting the results of an LCA or environmental product declaration, there is important information to identify in order to better understand the basis for how results are reported. One of the most important things to identify is the product category rule, or PCR, that was used. Product category rules define the requirements for life cycle assessments and environmental product declarations and are product category specific. In some cases, multiple product category rules may exist for the same product group but differ in their requirements. For example, the choice of system boundaries and the corresponding life cycle stages. System boundaries determine which life cycle stages and therefore which processes of the life cycle are included in the environmental product declaration. Furthermore, life cycle results are typically reported by life cycle stage. In some cases, defining system boundaries is partly based on a subjective choice made during the scoping phase. However, PCRs typically follow system boundaries defined by a well-known and accepted standard, such as ISO 21930 or EN 15804. Highlighted here are the defined life cycle stages from the product stage to the end-of-life stage. Some of these stages can be made up of hundreds of sub-processes. The major processes or steps in a life cycle stage are defined as modules. Highlighted here are the defined life cycle modules from raw material supply and manufacturing to use and disposal. A cradle-to-grave EPD, or environmental product declaration, must include all of the stages, while a cradle-to-gate EPD includes only the product stage, which includes raw material supply, their transport, and manufacturing. PCRs sometimes allow for a study to be scoped as cradle-to-gate with options, which is essentially cradle-to-gate that includes several but not all modules. Here is an example where more than one product category exists for the same product group, but different system boundary requirements for the environmental product declaration. In this example, the product category is for architectural coating, such as paint, powder coating, varnish, etc. In the International EPD System PCR, paints and varnishes and related products, the life cycle is broken down into three modules. Upstream, shown in orange, core, shown in green, and downstream, shown in blue. Results in an EPD following this PCR would be reported accordingly. However, the major processes within each module differ from those included in the life cycle stages defined by ISO 21930. As such, comparing two EPDs with different system boundaries as a result of the chosen product category rule is not possible, at least not without the modification of boundaries performed by the practitioner. It is important to note that results reported by stage or module may also not provide sufficient resolution into which key sub-processes are contributing the most to a final product's environmental impact. For example, we can't see the contribution from electricity use at the manufacturing facility or which raw material has the largest upstream impact. It is therefore important to understand which major processes are included, as defined by the PCR, and how they are reported in the EPD. One of the other most important things to identify is the functional unit that was used. The functional unit is a measure of the product system and provides a reference to which the inputs and outputs of the LCA can be related. A functional unit typically comprises a function, quantity, duration, and quality. The functional unit is basically a key element of LCA and can help enable comparison of two different systems for the exact same product category. For example, the functional unit of a chair can be one unit of seating to seat one individual maintained for a 10-year period. A declared unit may be used in lieu of a functional unit when the precise function of the product at the building level is not stated or known, or when the LCA is cradle to gate and does not cover a full life cycle. An example of this is dimensional lumber, such as a 2x4. The 2x4 can be used in a long-lived application such as commercial or residential framing, or in shorter-lived applications such as scaffolding. In these cases, a declared unit can be more appropriate, such as 1 kilogram of dimensional lumber. Let's say we're looking at two different flooring product EPDs, each following the same product category rule and using the same functional unit. In accordance with the chosen product category rule, the functional unit is 1 square meter of floor covering maintained for 60 years. The LCA results are therefore reported on the same basis. Although the functional unit here provides a comparable basis for measuring life cycle impacts of a product group, some product characteristics are not included, such as expected product lifetime. In the table at the bottom, the product lifetime characteristics are reported by row, and the columns report the corresponding value of each product. As we can see, although both fluorine products provide the same function, their expected product lifetimes drastically differ. Fluorine product 1 will need to be replaced 3 times over the 60-year period, while fluorine product 2 is expected to last the duration without any replacement. In addition to first and foremost identifying the PCR and the defining system boundaries and functional unit, one ought to identify the uncertainty surrounding the results of the EPD. Consider the assumptions made. Major assumptions, whether due to a lack of data, proxy data, or the use of secondary data for relatively large impact processes, may have substantially changed the outcome of the study. As a result, a sensitivity analysis for these parameters was most likely performed to better understand the variability of results and the importance of the assumptions made. If the uncertainty in results are not provided in an EPD, it may render interpretation difficult. Furthermore, the subsequent quality of data may have been reduced as a result. A low data quality means the results are not very reliable, and a high data quality means just the opposite. As such, this information should be identified if communicated in an EPD. In light of potential uncertainty surrounding the results of the EPD, one should also consider the LCA software that's used. In 2016, a study by Speck et al. Suggests that implementations of a supposedly common methodology in different LCA software can provide differing results. The paper claimed that were instances where reported impacts were greater than 20% for certain materials. Ultimately, as you look through the results of an LCA report or an environmental product declaration, there may be some surprising finds or exceptions to the trends discussed. Here are a few examples that we have come across. Generally, we would think that manufacturing has a larger life cycle impact than the use stage. However, this is not the case for some products. Consider carpet, which requires regular vacuuming and periodic steam cleaning. Depending on the traffic level, an increase in frequency for these cleaning methods become routine maintenance. Although one occurrence of cleaning is negligible over the entire life cycle of a product, the use stage becomes a larger overall contributor of environmental impacts after a 60-year time horizon, and in some cases, larger than manufacturing of the carpet product. Here are the global warming potential results pulled from an LCA study that was conducted for a carpet product. We can see that the use stage, while not larger than the extraction and processing stage, is larger than the contribution from manufacturing the carpet product. Another product with similar results are for flushometers. Flushometers are intended for use with toilet or urinal fixtures as the dispensing unit for the water supplied. The environmental impacts associated with use are due to the embedded energy in water supply, distribution, and wastewater treatment. Although the average flushing frequency in a day is negligible over the life cycle of a product, it creates a significantly larger overall impact over 10 years. It is important to note that energy intensity of water can vary depending on the geographic location, and that average flushes per day may vary as a result of location or fixture type. As a result, significant reduction of impacts can be achieved by reducing the energy intensity per gallon of water or reducing the number of flushes per day. Processes that have the largest contribution to environmental impact for one product may not be the case for another in the same product category. This can be seen for some steel products. Consider chromium steel versus carbon steel. Chromium steel is made from iron alloying mainly from chromium at a percentage typically greater than 10%. It is a corrosion-resistant product and is typically more expensive than carbon steel. Carbon steel is made by alloying iron with an amount of carbon between 0.5 and 2%. Unlike chromium steel, it runs the risk of corroding and is typically less expensive. The graph here shows the relative global warming potential for two different steel products of the same product group. Chromium steel shown in orange and carbon steel shown in purple. Both products are produced in an electric arc furnace, and results are expressed in kilograms of carbon dioxide equivalents per kilogram of product. We can see that for carbon steel, electricity used at the steel mill has the largest contribution to impact. Alternatively, in the case for chromium steel, ferroalloy inputs, which typically make up 15 to 20% of the product by weight, such as ferrochromium, ferronickel, and ferrosilicon, have a substantial contribution, if not the largest, to the cradle-to-gate environmental impact of the product. It is important to note that some published EPDs have excluded these alloys due to a lack of data, and this results in non-comparable or inaccurate results. Some higher quality and better performing products may have a larger upstream impact relative to its lower performing competitor, but ultimately have a lower total impact after accounting for the expected product lifetime. Consider powder coatings, for example. Powder coatings is used as an alternative to conventional liquid paint, where the coating is applied as a dry powder to a substrate and subsequently cured in an oven. Standard performing coatings can be used for light use without a lot of exposure and weathering, such as a lighting fixture. Alternatively, higher performing coatings can be used for heavy use with lots of exposure and weathering, such as stadium seating. The graph here shows the relative global warming potential for three powder coating products of the same product group. A standard performing coating, shown in orange, the higher performing coating, shown in purple, and the highest performing coating, shown in green. All products are produced in the same manufacturing facility and same coating application shop. Results are expressed in kilograms of carbon dioxide equivalents per square meter of product over a 10-year period. The product stage includes the extraction and processing of raw materials, transport of materials to manufacturing facility, and manufacturing of powder coating. The design and construction stage includes the transport of powder coating product to distribution center and customer. The use and maintenance stage includes the application and curing of powder coating to substrate and its use. Lastly, the end-of-life stage includes the disposal of the powder coating. None of the products here need to be replaced during this period, since they are all warranted to last at least this amount of time. We can see that the highest performing coating, shown in green, has the largest global warming potential compared to the other powder coatings. However, if we change the reference service life to a 60-year period instead of 10, which is the expected lifetime of a building, the results essentially flip. This is due to the fact that the standard and higher performing coatings have a relatively lower expected product lifetime than the highest performing coating and need to be replaced more often. This is despite the highest performing coating having the largest upstream impact relative to its lower performing competitors. As such, in some cases, a higher quality and better performing product may have a larger upstream impact relative to its lower performing competitor, but ultimately have a lower total impact after accounting for the expected product lifetime. Since there are exceptions to the trends and factors discussed, these surprising finds reinforce the notion that life cycle assessment is a powerful tool in understanding our built environment. While there are indeed some limitations in LCA, it does a great job at providing an entire picture for what may be occurring in the system. Much like a photograph, although slightly out of focus. We can just make out the content of the image and ultimately draw some conclusions about what we are observing. LCA is constantly improving to incorporate the latest science and metrics developed through vigorous peer review in the scientific community. We strive for a better harmonization of data, standards, and software to understand the many environmental trade-offs of a system and ultimately allow for a better comparison of products in our built environment. With the core concepts introduced in this webinar, you can apply a lifecycle lens to develop preliminary insight on the potential impacts of product systems in the built environment. Whether it's conducting lifecycle assessment, developing an environmental product declaration, or understanding complex environmental problems, we're here to help. Thank you for your time. I will now open it up for Q&A, and for further information, please contact Kim Vincent. Thanks.
Jeremy, thank you so much. I hope you guys got a lot of great content out of what Jeremy was saying. Just imagine being able to sit next to him nearly every day. It's awesome. We've had a lot of great conversations. So as he's been talking, we've had a lot of questions come in. Thank you so much. So I'm just going to start scrolling through them. Please feel free at this time, if you haven't already listed a question, to do so at this time. To start us off, can you walk us through what a typical LCA study would look like from beginning to end in terms of timeline? What's involved in putting one together?
Sure. So when we're going to conduct a life cycle assessment of a product, we typically work with the manufacturer to scope out which product category rule to use, depending on the products that are going to be covered, and also to scope out which products to include under the study. Once we've done that and established which products are to be included in the LCA study, we go through a data collection phase where we typically require primary data from the manufacturer, in some cases their suppliers, to better understand the weight of the product or the product characteristics, the lifetime of the product included, the resource use and emissions at the facility, where the suppliers are coming from and the modes of transport, as well as what their distribution network looks like. We require the material composition of their products by component or overall, as well as the type of packaging that's used. Recycled content is also taken into account. Once we've done that, we go through the modeling phase where we use typically LCA software along with a database to model this product system. Once we've done that, we do some sensitivity checks to ensure the reliability of the data, high quality data, and that it's representative of the product. And then we go ahead and make a life cycle assessment report, which is held in confidentiality between ourselves and our client. Once that's approved, we develop an environmental product declaration that's based on the requirements of the product category rule. It's a transparency document which summarizes the results of the LCA report, and that EPD gets verified through a third party and ultimately signed off and published to our website.
Great. Thanks, Jeremy. Another question is, how long does it typically take to do these kinds of studies?
It's a good question. Typically, studies vary in how long they do take. Cooperation with the client in terms of how fast we can get the client data, those are all factors that need to be accounted for, but typically around 2 to 3 months or up to 4 months for some projects is how long an entire life cycle assessment takes, even in accounting for the development of the EPD.
Okay, if I've interpreted this question correctly, I have multiple manufacturing sites. How do these get accounted for in an LCA?
So what we'd like to do is understand the types of products that are being developed at the manufacturing sites. If one facility is producing a specific type of product that's included within the scope of the LCA, and another facility is producing an alternative type of product which is also included, we would need to account for that. If there are two facilities located in different regions producing the same products, what we would need to do is allocate the amount of resources and emissions associated with the production of each product at each specific facility, ultimately creating a weighted average in a sense. Some facilities are larger than the others, so the annual facility production is accounted for to perform allocation method, basically allocating the amount of resources to produce one product based on the total facility production over a year. Okay, great.
Next question, good one. What about land use and habitat alteration impacts? These impacts vary widely for extraction of different products.
So this is true. And when we're doing life cycle assessment for the development of a environmental product declaration, we refer to the product category rule. And in the product category rule, there is a requirement for which environmental impact categories we need to include or need to assess and ultimately report. The product category rules that exist today typically, and I'd say for the most of them, do not account for this, unfortunately. So while life cycle assessment isn't limited in that regard, the method and what's required of us to report is, in a sense. Ultimately, what we'd like to do is extend or increase the scope of which environmental impacts are being reported so that we can account for alternative impacts that, aside from the 5 typical impact categories that we are required to report, such as global warming potential, acidification, eutrophication, ozone depletion, and so on. So while impact categories such as land use and habitat alteration are important and ought to be considered, they are typically not considered in current environmental product declaration development right now.
Next question, and feel free if you have a follow-up to that to ask that offline. We're happy to talk in more depth about that because we've done a lot of development around methodologies for life cycle to account for habitat alteration and land use. Next question, you mentioned you developed PCRs. You don't use PCRs already developed for, let's see, maybe I might not be getting this question correctly. You mentioned you develop PCRs. You don't use PCRs already developed for the products, if available.
I can try to interpret this question. So we have in the past developed product category rules in-house. Right, we have a North American steel product category rule that was developed here. We're always looking to expand how we do business here at SES, and development of product category rules, if they don't exist, would be in our best interest. So for a business opportunity, yes, we are always considering PCRs that currently do not exist but might be available in the future.
And if I were to interpret that question a little bit differently, if we swap around the verbiage, don't you use PCRs already developed for products if available? And yes, if a PCR is already available for a product category, then we rely on that PCR, assuming that the validity of the PCR is still in check. If there are several PCRs due to expire this year, and so there are efforts underway by various program operators to make sure that those remain up to date. The Program Operator Consortium has a wonderful listing of all of the PCRs that are available at programoperators.org, which we are a part of. And there you can find a list of all PCRs that are available for use in North America, and also those that are due to expire or that are undergoing update. Next question is, we are an importer-distributor. Do we need to go to our vendors and eventually their suppliers to be able to pick up a full cradle-to-gate for our product lines?
So that's a great question. Typically, no. While it will increase the resolution of your system in terms of the results, it'll be more representative of your product to get a primary data from your suppliers. Product category rules typically do not require the use of primary data collected from your suppliers in order to do a cradle-to-gate or even a cradle-to-grave life cycle assessment. However, some product category rules do exist that require it, but it is quite rare. That being said, no. A quick answer to that, but it would, however, increase the resolution and better understanding of your system.
And a follow-up question to that is, What typically does that do to the timeline? Does that affect the timeline at all?
It would affect the timeline depending on the number of suppliers that you have. If we're looking at 20 different suppliers versus 5, then it would increase the length duration to collect the data and ultimately put together a model for that.
Okay. And to follow up this question, I believe I just answered, is there a central repository for product category rules? Yes, there has been one created through, if you go to programoperators.org, and I can follow up and send out that link, there you will find a list of all the PCRs that are available. A great resource. It also lists a whole bunch of EPDs that are available by program operator. I believe it excludes UL at this time. UL has a spot database, but it includes all the other North American EPDs as well.
And to follow up, I mean, if you are a distributor and an importer, typically we are required to conduct a lifecycle assessment with primary data for the manufacturing of product. Upstream from that, however, it's typically optional to collect primary data from their suppliers.
Thanks, Jeremy. All right, we have a few more minutes, but that's all the questions we received for now. If you have any final questions, please do shoot them over to us. And if you have any questions that come to you afterwards, feel free to shoot me a quick email or give me a call. I'm happy to, or for Jeremy for that matter. This webinar was the first of a series as a part of the Program Operator Consortium, and there will be one coming up. The date has yet to be announced, an exact topic yet to be announced, but we are excited to bring you this education because we're hoping that through sharing our knowledge, there will be a general increase in education or knowledge in the marketplace with which to better understand EPDs in their context. All right, it looks like we are pretty much wrapped up. Thank you so much for joining and for your attendance in today's webinar. Again, this is being recorded and we will send it out to you afterwards so you have it for your records on file. Thanks, Jeremy, so much for your time today and for imparting all this knowledge onto us.
It was my pleasure, and I thank you all for joining, and hopefully we can stay in touch. Thanks.
Bye.